Okay, so I'd like to welcome you all to this morning's session. It's a great pleasure for me today to introduce Ralf Hiptmeyer from the ETH Zurich. I guess I've known Ralf for more years than we really either of us would care to mention. I'm a big fan of Ralf and his work. If you've never read one of Ralf's papers, I would strongly encourage you to do so, because every single word is painstakingly thought about in there. The content, of course, is very good, but I particularly enjoy his papers because I always learn a new English word when I read his papers as well. Ralf did his PhD at the University of Augsburg and started off quite spectacularly. I think he was the first to really get a convergent multigrid algorithm for Maxwell-type equations before most people even knew about Nedelec elements and so on. He won a prize for that paper. His work's characterized by working on hard theoretical problems, and his career has shown that, and he doesn't just work in one area, so he's worked in multigrid, he's worked in integral equations, he did some work with Jin-Chao Xu on the auxiliary space multigrid method, which I believe is solving bigger problems than any other multigrid algorithm. And today's no exception. He's going to talk to us about a very important theoretical tool for the analysis of high-order methods. So without further ado, I'd welcome Ralf to give your talk.
Well, thank you, Mark. Thanks for advertising me as an English instructor, but this is not my intention today. And thanks for not disclosing that so far my research was has been hardly concerned with higher order methods. This topic represents about the only foray into this field that I have ever made. It's joint work with a collaborator from industry, Clemens Pechstein from Linz. However, it will be heavily focused on theory, and I leave it to you to consider this a promise or a threat. Of course, there will be many technical details, and I cannot dip into them. So the topic is a topic that is addressed in many other presentations at this conference. It's about structure preservation. Structure preservation on the technical level. And second objective is to present to you a range of theoretical considerations and tools that I consider useful and exciting. Of course, technical details cannot be covered here. You can look them up into this long report that gives you everything that you want to know about the last comma. Well, this is a presentation about theory of regular decompositions, discrete, boundary-aware, and p-stable. And the last attribute is linked to this high-order connection. Of course, first, I have to establish the framework, the spaces involved, then resolve the mystery of regular decompositions, and then address two variants of them in the discrete context, what I call the H-version and the spectral version. So the functional framework is by now fairly familiar in the numerical analysis community. It's that sequence of spaces in 3 dimensions that is closely linked to de Rham cohomology. This is the de Rham cohomology in 3 dimensions expressed as a sequence of Hilbert spaces. It involves the fundamental differential operators, gradient, curl, divergence, and for domains with a trivial topology, this is an exact sequence. So the kernel of the curl is provided by the gradients, sloppily speaking. There's also a version of this sequence that respects 0 Dirichlet boundary conditions. of course, of the right type for each space. And under some more complicated assumptions on the topology also, this is an exact sequence. Of course, everything can be understood from a more general perspective, appealing to exterior calculus, so the calculus of differential forms. Then it's written like this, but don't worry, I'm not going to develop things on this level today. So this is the functional framework. And there's deep algebraic structure behind this. This is one of the, well, say, main discoveries of modern mathematics, in my opinion. And it was also an important discovery that there are discrete finite dimensional counterparts of these sequences. The first to be discovered were the Whitney forms, well, initially as a tool in differential geometry. So they are actually finite elements. They require a triangulation, and I'm going to restrict myself to tetrahedral meshes of a 3D polyhedral domain. And then we can find a family of, say, spaces of piecewise linear functions or vector fields that, when equipped with the right local degrees of freedom, so the local degrees of freedom are certain integral expressions, well, some integrals over edges, over faces, over the volume, and when you define them properly, then it's possible to use them to glue these local spaces of affine linear functions into subspaces of the function spaces. And what you end up is this structure. And in particular, what you end up is the theorem sequence on the discrete level, because it turns out that in the case of trivial topology, also these spaces of Whitney forms, they form an exact sequence connected by the very same differential operator that also connect the function spaces. And I've also indicated that they are genuine subspaces, so they respect the compatibility conditions implied by the definition of the function spaces. This is a fundamental structure, an algebraic structure. And this is a prime example of algebraic structure preservation in the construction of finite dimensional entities. This is lowest order. Then over the years, people discovered that it's possible to generalize this to piecewise polynomial spaces of arbitrary degree. Again, I assume tetrahedral meshes. And what was discovered is, well, for degree 0, it's just the usual Lagrangian finite element. They can go up to any degree. Degree 1, it's Nedelec's construction. Degree 2, Raviat-Thomas elements. And degree 3, well, just discontinuous polynomials. And the great thing about these spaces is, well, first of all, can equip them with zero boundary conditions, but secondly, oh, well, I should have mentioned this. All these spaces were somehow introduced rather independently, and then later unified under the phrase of finite element exterior calculus. They are understood as discrete differential forms, and then their construction is fairly natural. And then it's also natural that you've got this connection, this algebraic structure also for the higher order case, namely the discrete theorem sequence P-version. And what other devices finite element exterior calculus gives you is nodal interpolation operators that also connect the spaces and that enjoy this commuting diagram property. I'm coming back to this later. Again, perfect preservation of algebraic structures. But I'm not so much concerned about algebraic structure preservation. My talk is concerned with what I would like to call metric structure preservation. And this is connected with regular decomposition. And now let me explain to you this mysterious thing. Well, the starting point is Helmholtz decomposition of function spaces. Let's recall the function spaces. Well, I'm going to focus on H curl conforming vector fields. And all of you know the Helmholtz decomposition. Since the range space of the gradient is closed in L2, you can orthogonally decompose L2 vector fields into gradients, curls, and maybe some cohomology space. This classical Helmholtz decomposition. This classical Helmholtz decomposition can be restricted to H curl. You split H curl into gradients and their L2 orthogonal complement in H curl. This can be done for the full space. It can also be done for the space with boundary conditions. And now, a key observation is that the complement space of the gradients, this is here denoted as a subspace of H diff intersected with H curl. This space enjoys some higher regularity. More precisely, in the case of nice domains, this will be a subspace of H1. However, in case the domain is not nice, in case there are reentrant corners, this inclusion breaks down. And now the key idea is to sacrifice L2 orthogonality in order to preserve this nice regularity property. This is the key idea behind regular decompositions. Regular decompositions try to save H1 regularity at the expense of orthogonality. They provide splittings of H curl, no longer L2 orthogonal, but stable, and with an H1 component, H1 vector field component. Well, formally you can write it like this, but I prefer this notation. Or you can remember this regular decomposition theorem as the phrase that gradients fill the gap between H curl and H1. So this was first introduced as a tool in PDE analysis, and over the years has turned out to be an extremely powerful device also in numerical analysis. Now there are tons of papers where this is used for one purpose or another. This regular decomposition. So H curl is stably split into an H1 subspace and the gradients. Well, there are results for other spaces, but let's focus on this. How can this be proved? Even in the presence of boundary conditions, a brief sketch, you have to extrude the Dirichlet boundary. I call this insertion of a bulge. Then you need a lifting lemma on the whole space. Why do I call this a lifting lemma? For a vector field, it provides an H1 vector fields with the same curl on the whole space. You prove this using Fourier techniques. And this lifting lemma combined with extension to the whole space and then extension back into the domain finally gives you the proof of the regular decomposition theorem. So it's not very difficult once you have the idea to use this lifting lemma on the whole space. Well, and the stability estimates in the lifting lemma give you the stability of the proof, no, of the decomposition. Well, I learned this in this paper. All right. This is the continuous regular decomposition theorem. This is what I call metric structure because its key property is its stability, so that you split the space into components whose norms can be controlled. And now we want to see whether, also on the discrete level, on the level of the finite elements, such things can be found. This is now the quest for discrete regular decompositions. Let's first address the H-version, Whitney form's lowest degree. This is the regular decomposition theorem, and it tells us what we should aim for. We should find a discrete counterpart. So we first have to settle the issue, what is the counterpart of these H1 vector fields? Well, this is not particularly difficult, because the natural choice is, say, piecewise linear continuous vector fields in each component. This is what I call VH. This is the subspace of H1 vector fields. This is what we want. I've put a question mark here because we are not yet there. This would be a perfect discrete counterpart. We start from a finite element function, the VH, and then we would like to have a splitting of the VH into a ZH and a gradient of another finite element function. This is the algebraic structure behind the regular decomposition theorem. However, we would like to have stability as well. And in particular, we would like to have stability H uniformly. This is indicated by this wiggle inequality. The wiggle inequality in my presentation invariably means uniformity of estimates with respect to discretization parameters. So we want to have these estimates uniformly. And now you see, this is the ultimate goal. We want to have, also on the discrete level, the same nice stability properties as enjoyed by the continuous regular decomposition. All these uniform bounds on the norms of the components of the decomposition. Well, now let's see whether we can get there. This would be preservation of metric structure. Uniform bounds on the norm, uniform stability on the discrete level. This is the next step beyond preserving algebraic structure. Well, side remark. Well, this cannot be achieved even on the algebraic level because we don't have this inclusion in general. Well, we can easily fix this introducing some projector. Okay, let's put up with this. Now, let's try to prove it and then see what we get. This is a sort of this simple old proof. What we need is a special interpolation estimate for H interpolation. Remember this, for H elements, the interpolation operator relies on H integrals. Well, this immediately tells us that we cannot hope to get such an estimate. Why? Well, H integration is not a bounded functional on H1. So this is not possible. However, it turns out that an exotic version of such an estimate is possible once you restrict the curl of V, say, to polynomials. So the curl is now discrete. And then we can obtain such an estimate. This was a key tool in the proof. You cannot get this to be L2 stable, no matter what you impose on the curl. Not possible. All right. Secondly, ingredient is the well-known, meanwhile classical Scott-Chung quasi-interpolation operator. So this is a boundary-aware H1 stable projector onto the space of piecewise linear finite elements. All right. Now let's put these ingredients together and mix it into a proof. Also, this quasi-interpolation operator is not L2 stable. Keep this in mind, okay? It's natural to start with the continuous regular decomposition of the finite element function. VH is a finite element function, but once you consider its regular decomposition, what you end up with is no longer contained in finite element spaces. It's not possible. So we have to tweak this. And of course, we will use the interpolation operators and projection operators. And what is very important is that, of course, the curl of Z is the same as the curl of VH, so it's discrete, piecewise polynomial. So we can use this exotic interpolation error estimate to estimate this interpolation error for the H interpolation. And the second ingredient now is the quasi-interpolation that is used to push Z into the finite element space. And this is now all well put together in a smart way. Then we can split Z like this. We notice that the last term is curl-free, thanks to the commuting diagram property of the H interpolation operator. And this makes it possible to find, a discrete potential for this expression. So this provides the gradient component. And then you can use triangle inequality to estimate everything. However, as you see, there's a guy coming up, which is not really desirable. This is this VH tilde. One finds that the VH tilde is somehow asymptotically small. Its norm can be estimated, but it's something that is present here that pops out of the proof, which shouldn't be there in a discrete regular decomposition. However, we get it from the proof. So what we have obtained so far is this kind of discrete counterpart, this one, with this extra term that I call, say, local garbage. It's an interpolation residual term. It's small asymptotically, but it's there. Another shortcoming is that the stability is not really perfect. At least we have this stability for Z in the H1 norm and for phi in the L2 norm. Okay. And the smallness of the tilde component. So this was the result until 2 years ago. Meanwhile, Falk and Winter achieved a major breakthrough in discrete exterior or in finite element exterior calculus. They managed to construct these commuting bounded cochain projectors. So what is this? It's a sort of quasi-interpolation for these discrete differential forms, and it's a suitable replacement for the H interpolation operator. It's a family of projectors that enjoy perfect stability. Not like the edge interpolation operator, well, that we could tweak at least to be stable in H1 under some assumptions, but it will never be stable in L2. This one is. And there's a family of them, and they enjoy the commuting diagram property, like the standard interpolation operators for, well, discrete differential forms. Nice. This can replace the edge interpolation operator in the proof. And there was another development that allowed us to relax the or to replace the classical Clément interpolation operator, was called Chang, with a generalized Clément interpolation operator that is even stable in L2. Call it MH, and it has this nice stability. Well, and now mixing these ingredients into the proof, of course, you get better stability. You get this new discrete regular decomposition theorem. We still have this local garbage, because no matter which interpolation or projection operator you use, there will always be a residual quantity, always an interpolation error. And this is collected into the tilde term. And we could not get rid of this. At least now we have this stability. And of course, all the other norm estimates stay intact. This is the latest version of the H discrete regular decomposition theorem. Very nice stability properties, however, not so nice in terms of the presence of this tilde term. Nevertheless, extremely useful, also already in its old version. It has been used, well, to prove a lot of results connected with discrete differential forms. It's for multigrid theory, proofs of convergence of domain decomposition methods uniformly in the mesh width. Then this auxiliary space preconditioning technology was a direct offshoot of the theoretical developments. It can be employed in the analysis of a posteriori error estimators and even for understanding well, boundary element methods. So a very versatile tool, so really worth knowing if you work in fields connected with discrete electromagnetics. This was the H-version. But now, to pay tribute to the title of the conference, of course, I'm supposed to talk about higher order versions, P-version. And this is a recent, well, result that I achieved together with Clemens Pechstein, P-version. We have seen the P-version of discrete differential forms, Nedelec spaces, Raviat-Thomas spaces, and of course, higher order Lagrange fine element spaces. They form the P-version sequence of discrete differential forms. Now, what should we strive for? Essentially the same as in the H context, except for replacing H uniformity with P uniformity. Recall the regular decomposition theorem for H curl with zero boundary conditions, with its nice stability features. Natural fine element space for the Z component, of course, again, component-wise, Lagrangian finite elements of degree P. This is now the V space. So it's just vector fields, continuous, piecewise polynomial of degree P. And then we would like to get such a result. For each p degree discrete one form, we can find, well, this set P in the H1 conforming degree P space and scalar potential phi P so that they combine into Vp. Of course, you take the gradient of the scalar potential. And most importantly, apart from this algebraic structure preservation, we would like to have P uniform norm estimates. Norm estimates that perfectly mirror the norm estimates that we have for the continuous regular decomposition. Same story as before. I'm repeating myself. This was a cut and paste job, replacing H with P. Okay. Now, let's see how far we can go. As you will already guess, we won't get that far, but almost. And on the way, we will come across some really fascinating theoretical tool and also recent developments. The first one was a well, sort of breakthrough discovery made by Costabel and McIntosh. Smooth Poincaré liftings. What is a Poincaré lifting? It's a special case is this one. This is an explicit formula that gives you a vector potential for a divergence-free vector field. This is stated in the orange box below. So when you take the curl after you've applied this Poincaré lifting, you recover the vector field if it was divergence-free. So it's a constructive proof of the existence of vector potentials. All right. This guy has bad mapping properties, not so nice. So it was considered not so useful for a long time. But there's an easy fix that was, of course, first discovered in PDE analysis, and then by Costabel and McIntosh generalized and really well put in the Sobolev context. The discovery was that this parameter point A can be used to improve the mapping properties by just a simple averaging technique. You define a smooth Poincaré lifting by averaging. And now this mapping, smooth Poincaré lifting, has amazing mapping properties. For instance, now it maps continuously from L2 to H1. And it still provides a vector potential, of course. And now a subtle observation, but of fundamental importance in the finite element context is this guy preserves polynomials. So it will respect the structure of the finite element spaces. This is one ingredient. Second profound tool is projection-based interpolation. First pioneered by Leszek-Demkowicz, and there's a sort of latest results by Markus Melenk and collaborators that have now refined the interpolation error estimates. And this is what I'm going to use. What is projection-based interpolation? It's a formidably technical generalization of what I've introduced as edge interpolation for the lowest order case. For the lowest order case, projection-based interpolation is the standard nodal interpolation operators for Whitney forms. And now this is the logical generalization to arbitrary degree. It's a very technical construction. I'm not going to give you details. I give you properties. We can find interpolation operators for arbitrary degree P and for the whole sequence of discrete differential forms so that they are projectors. They enjoy the commuting diagram property again, like their lowest order counterparts. And they are perfectly local. So they're really local interpolation operators. Locality comes at a cost. And the cost is that their continuity properties are not so nice. However, well, we can get interpolation error estimates for them, assuming sufficient regularity for the argument vector field. So this is, for instance, the case for, well, standard Lagrangian finite element spaces. Then you get this interpolation error estimate. Well, very explicit in P and H because of locality. So this is second ingredient. And it can, oh, sorry. No, what? Sorry. No, this is going back. And this can be used to generalize this exotic lemma, this interpolation error estimate under a constraint on the curl, to the spectral setting. Because now, if the curl of a vector field, of an H1 vector field, is discrete, then we have a P-uniform estimate like this. And how can this be proved? Just a few steps. We plug in the smooth Poincare lifting. Why can we do this? Well, we can do it because it preserves polynomials. Here, this interpolation error vanishes for, well, discrete fields. And the B applied to curl U is discrete. So this doesn't change anything. But this guy is curl-free. Well, because B provides a vector potential. So it can be written as the gradient of a potential. And then you apply the commuting diagram property, and then you're done. Then this boils down to the estimate above. So it's really easy once you have this smooth Poincare lifting available. Third ingredient, it's P-uniform quasi-interpolation. There's this paper by Karkulik and Melenk, which took me a week to read, but it's in terms of technical content, it's really fascinating. What they do is they elaborate a very intricate but powerful modification technique. And we could really use this very well. What do we want? We want a quasi-interpolation operator, P-stable, that also respects boundary condition. So the idea is to use a mapping that maps into this, what I call the bulge domain. So a local retraction to the bulge domain. This is a sort of geometric construction. And then use the idea of mollification, of local mollification, so the convolution with a smoothing kernel. And this you assemble into a local projection operator that also involves some very rather primitive interpolation operator, in fact. But since it acts on the mollified function, it need not have good properties. But the whole thing will have good properties. This is quasi-interpolation operators that respect boundary conditions on the Dirichlet boundary, and they have great stability properties, both in L2, in H1, and of course then also approximation properties. And now we have these three ingredients. We have this exotic interpolation estimate for the projection-based interpolation. We have this replacement for the Clement interpolation operator in this p-uniform quasi-interpolation. And now we can plug this into the old structure of the proof. And what we get is the p-version of discrete regular decomposition. This one. This is the algebraic structure. So we have a splitting of a p-degree discrete 1 form into this regular component. So the projection of an H1 conforming vector field. Then a gradient. But unfortunately, as in the other setting, there is an interpolation error, and it introduces this tilde component. From the p-uniform estimates for the projectors and the interpolation operators, we get the nice stability properties. However, the, well, a bit poorer stability properties of the projection-based interpolation still bars us from getting L2 stability. So there's one estimate missing. But at least everything is p-uniform, and this tilde component is p-asymptotically small. And this brings me to the conclusion of my presentation. There are still things to be fixed. The p-version works for uniform p only, for a technical reason that is really annoying. There's no HP version. I'm not going to tackle this. Too lazy. And there is these tilde contributions. I'm not sure whether one can get rid of them. Can we tidy up the garbage? It's not clear. But I hope, nevertheless, I've shown you some interesting theory. What I've shown you is quite a few very interesting and deep techniques in the numerical analysis connected with discrete differential forms and also beyond. So some of them are really worth studying because they can be used in various contexts. And that's all I have to say. Thank you.
So we have time for a question or two. I also should announce that there's going to be a short test on the material in this talk before you're allowed to leave the room.
Sorry, I'm just wondering, I know there's this result about Helmholtz decomposition for polynomials on the infinite domain, namely, that it's non-unique. Do you think that explains some of your problems with the local garbage, or?
Uniqueness is never an issue here because regular decomposition, when you just impose stability, well, you've got an infinite number of them. So, well, the non-uniqueness at least can give some hope that it's possible to get rid of this garbage terms.
Oh, okay.
So we could never find an argument that would rule out the absence of garbage terms. But we could never, on the other hand, we could never find an argument that could really get rid of them. So it's not yet decided, at least as far as I know. Maybe somebody's got an idea to demonstrate that this is inevitable. This would also be a result.
Thank you for your talk. I was wondering, most of the theory here typically applies to linear equations, right? Is that true? The stability proofs?
This what I've shown you has actually nothing to do with any equation. There's no PDE that I have addressed. Of course, the application context is, first of all, linear Maxwell's equations and linear grad diff equations, but it's about spaces and Feynman spaces, and whether you apply them in a linear or nonlinear context is up to you. Of course, the focus of research so far has been on understanding the linear equations, because this is what you start with.
So,
however, you can probably, if you're creative, also use these results for understanding some nonlinear phenomena, but I'm not going to comment on this because I've no idea.
So any further questions or comments?
So thank you for this wonderful talk. So as you mentioned in the talk that you go back to the tools of Costa-Bell and McIntosh for the construction of these lifting operators into polynomial spaces. So we were also interested in constructing lifting operators back into H-diff spaces. And what we noticed there was that for general polynomial data, it's not entirely clear if it's possible to get the stability required, except if we actually increase the polynomial degree of the space into which we want it to lift. So right now it's still an open question. So my question to you was, do you think that maybe this garbage terms might be to do with the adjustment of the polynomial degrees? You might want to lift into a slightly bigger discrete H1? It's a bit of a speculative question, really.
Well, by magic, the Poincaré lifting just lifts into the right spaces for discrete differential forms. So there's no excess polynomial degree if you, as I have done, consider the first family. The garbage term has nothing to do with the Poincaré lifting. It's a residual term introduced by the interpolation error of the quasi-interpolation of this H1 vector field. This is the actual source of the garbage terms. It's not connected with the Poincaré lifting in the P context. It's introduced by the quasi-interpolation.
I think all that remains is to thank Ralph for, I think, what was a remarkable talk for its range of technical ideas. I think this has got a lot of material. It'll take a lot of time to absorbed by most people, but I think that this is really a breakthrough, and this will become very important in the years to come. And I'm sure this is going to generate a lot of clicks on YouTube. But let's thank Ralph one more time. Thanks very much.